that they will ask?
And they will be appear on, sir, YouTube.
Acha. So YouTube, I have to log in or no?
Yeah, one of the your TA can log in.
Okay, okay.
Sir, start it.
There is
Okay, hello everyone. Uh, this is the live session for Analog Electronic Circuits NPTEL NOC 2020. And I already have a few questions from you in advance. So there are three common questions. That is, please discuss about the exam pattern. What is the level of difficulty in the exam? And will our assignment help us in solving the exam questions? What sort of questions should we expect in our exam? So there are multiple questions which are exam related. I think about four such questions are there. So exam questions, my general advice is that if you follow the assignments, so I know assignments have been given, uh, you would also know the answers to the assignments. Those have also been given, provided. Now, if you can uh, understand these assignments based on the answers, right? Try to resolve them based on the answers. If you study the worked out assignments, you will, the exam will be easy. So I would say, strongly recommend study the worked out assignments. Okay, this is the number one single most important thing to do as far as your exam is concerned. Exam, you absolutely have to study the worked out assignments. Now, beyond that, what is the question pattern? So the question pattern will be, so we have in NPTEL, they have a set, there are some rules. Rule number one is that 40% should be recall type. Rule number two is, so this has nothing to do with me. This has to do with NPTEL. So it's something like this. So there will be 40%. So 40 marks will be based on recall. That is something that you will have to remember from the lectures. You'll have to plug it in and you'll get the answer. Then, so these will be small. Uh, there will be roughly 22 mark questions. All right. So roughly 22 mark questions will be there, and that will be 40% of the exam. And the remaining 60% of the exam will be 6 questions. So remaining 60 marks has 6 questions, each 10 marks. And each of these 10 mark questions has actually 5 parts. All right. So basically there will be 6 questions, 6 problems, and each of these 6 problems will have 5 parts, each worth 2 marks. So basically, in total, there will be 50 questions, each worth 2 marks, right? The first 20 will be recall type, and the remaining 6 into 5 will be actually 6 10-mark questions. So this is the pattern of the exam. And how do you study for this exam? You study the worked out assignments completely. All right. So that's the single most important thing. Fine. Now, I have uh, a few more questions. The important ones over. So the important one is um, I am having a problem in analyzing output impedance and transconductance. I need a better understanding regarding output impedance and transconductance. So all you have to remember is that what we are talking about is nothing but the Norton equivalent. So as long as you remember that this is the Norton equivalent, then everything is going to fall into place. So if you have a block, circuit block, okay, how do you find out the Norton equivalent? Norton equivalent is you've got a port, one port coming out. So problem number one is driving point impedance. All right. So when you want to find the driving point impedance, inside this, there is probably, not probably, there is an input voltage. Okay. Your input to the amplifier. So this is your amplifier inside. Maybe this is a common source stage or common gate, whatever it is, right? It doesn't matter. So this is your amplifier. This is an input voltage source or input current source. So when you want to find the driving point impedance, the first thing that you have to do is make this input source equal to zero. That is, you have to short circuit it. All right. So you have to short circuit the input source if it's a voltage source, especially if it's a voltage source. If it's a current source, then you have to open circuit it because 0 amperes current means open circuit. 0 volts voltage source is a short circuit. So if it's a voltage source, then you short circuit it and then you look inside and find the resistance. All right. So this is your output impedance. So this is number one. And number two that you have to do is you have to find out the short circuit current. So this is what you do to evaluate the Norton equivalent of a circuit. So you find out the driving point impedance and you find the short circuit current. So how do I find the short circuit current? Now you revive this voltage source. So you bring it back to life, you bring it to life, right? Now this should be your voltage source V in. And now you have to find out the short circuit current. You apply a short over here and find the current. Okay. Then the overall model is going to look like this. I short circuit, which you have measured. And this one, let's call it Z out. So this becomes the model of your circuit. All right. Now I am talking in the air, of course. This is all very general so far I have given, right? The question I really think is more to do with specifics, right? the student who has written the question says that I am having trouble in finding the output impedance. I am having trouble in finding the short circuit current. The no, I am having trouble in finding the output conductance. Okay, so sorry, I'm the trans. Uh, I'm having trouble in finding the transconductance, output, analyzing output impedance and transconductance. All right, so that is the question. So I know I haven't yet answered the question. The first thing is that as far as transconductance is concerned, this is what you have to find out. You have to find out the short circuit current using Norton's technique. Right, what is Norton's technique? You connect the two out the output port, you short it, measure the current. Right, don't think of it as trying to measure transconductance. Think of it as trying to find the Norton equivalent of the circuit. You'll be able to find it. The other part, finding the output impedance, has some shortcuts. So what are the shortcuts? The shortcuts are two formulae that we have. Right, we have two formulae. These formulae you have to memorize. Right, and this is the only thing that you were supposed to memorize in this course. So one is this and the other is, so there are two formulae. All right, in the first picture, in picture number one, so let me call it 1 and 2. In in this picture number 1, the input is applied over here, but remember, this picture is for measuring, I mean, the formula is for measuring the driving point impedance, the output impedance. In that case, this input has to be nulled. That is, you have to make it 0 volts. So therefore, I mean, you can apply the input here, of course, but as far as measuring the impedance is concerned, this input becomes 0. Okay, because it's a short circuit. Similarly, in case of in set in the second setup, you are supposed to apply input over here, but I mean, remember, when you are finding out the resistance, you have to short circuit the input. So really, you are going to kill this and short it out. All right, and then you have to find the input impedance, and this formula is given. This one formula is RDS plus RS plus GM RS RDS, right, or however you want to put it. And this, in the second case, the formula is RDS plus RD divided by 1 plus GM RDS. All right, so there are these two formulations, and you basically try to utilize these two formulae. You'll see that everything falls into place when you start using these two formulae. So, for example, let's say you have the hardest example is this one. This is the hardest example. All right. And in this hardest example, when you look upwards, you see RD. When you look downwards, you see something that is just this formula. So your net output impedance is RD in parallel with, all right, basically you just write it down. This is the hardest one, right? What about the short circuit current in this particular, in such a case? What, how will you find out the short circuit current? Turns out that to find out the short circuit current, you can actually take the help of other things. So when you, first of all, you, to find out the short circuit current, the short circuit transconductance, right? You have to find out the current over here. Okay. So if I connect this to ground over here, immediately the current through RD becomes equal to 0. So you forget about it. There's no current in RD. Both sides of it are connected to ground, right? And now you have a situation where you have, this is pretty much your situation. So if you know the voltage over here somehow, if you can find out the voltage over here, then the short circuit current is nothing but this current. So if this voltage is, let's say, Vs, if I somehow manage to find out what the voltage Vs is, then the short circuit current is Vs by Rs. All right. So now we look at this sub problem. This is actually the hardest case I am analyzing. So this is not going to be easy. Let me finish. Right. This is not the end of the story. So I have broken up this short circuit problem into a sub problem. The sub problem is, what is the voltage over here? Because if I can find out the voltage over here, then I have the answer. All right. Now, how do you find out the voltage over here? In this sub problem, again, you find out the output impedance and the short circuit transconductance. How do you find out output impedance? Now you look in from here. All right, you look in over here into this circuit. I need to find out this voltage. So I look in over here. I see two things. Looking down, I see RS. Looking up, I see this second formula but terminated by 0 ohms. So my impedance is going to be Rs in parallel with Rd is 0. So Rds by 1 plus GMRds. Okay, so this is the output impedance. And then again, I find out the short circuit current over here. Right? Why am I doing all this? To find out the voltage over here. So now I do the short circuit current. This is the two-step method. Right? Now Rs will fly away because there's no current through Rs. Right? And now the question is really simple, because inside the MOSFET there is just GM. Right? What is the current through RDS? Both sides of RDS are connected to ground. So inside the MOSFET there is just GM. So this short circuit current going this way is GM times V in. So I have found out the model for this circuit is, This is now the model for this sub problem. Now, if this is the Norton equivalent model, then what is the voltage? I can now find the voltage. The voltage is this current times this resistance. That gives me the value of Vs over here. Okay. And therefore, the short circuit current over here is going to be Gm by Rs times Rs in parallel with Rds by 1 plus Gm Rds. All right. So this is the two-step problem. Now I have found the short circuit current in the original problem. I know the output impedance of the original problem. Okay, so this is typically the hardest case. I solved the hardest case for you. I hope this is now going to resolve your problem of uh, difficulty in finding out the short circuit current and the output impedance. Okay, I hope you have followed. All right, now I'm going.
So your voice is not coming. So I can't hear you. Still can't hear you. No. No, no, sir. Not yet. So something is wrong. We can't hear you. No. So can you leave the meeting once and join back? Yes, sir. So still you are not audible.
I audible now?
Yes, 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 sir. Very much.
Okay, great. Sorry, I think something went wrong. Okay, uh, so I will now move on to the next question. The next question is, please explain various types of filters made with the help of RLC, and please tell me which book should I follow. I am a student currently in third year. So for this particular course, first of all, uh, filters is not really part of the agenda, but with RLC you can. So basically there are four types of filters: 4 plus 1 variety of filter. What are the filters? So the four main filters are low pass, high pass, band pass, and band stop. So low pass typically has a structure that looks like this. Okay. So the idea is,
Yes, sir, your pad is not seeing.
oh, okay, sorry. I need to share again. Am I still audible or have I knocked out?
Yes, sir, you are still audible.
Okay. Is the pad visible now?
No, not yet.
Not now, sir.
So something went wrong once again.
So in the meanwhile, you can look at the chart and you can answer some of the questions.
Yeah, yeah. So there are basically four types of filters. And uh, no, I'm not able to see the chat also. So if you can tell me the question.
Okay. So one one student wants. So there are some questions. So now your video is hung up. Um, so we can't see your video anymore.
Mode, then automatically this will behave like a low pass filter. The second variety of filter is high pass filter, where the inductor is, so is the screen visible now?
Yes, the screen is also visible and your voice is also visible.
Okay,
I
excellent,
mean,
excellent.
we can hear you. I mean,
Okay, excellent. So this is the first type of filter. This is the low pass filter. The high pass filter, you basically replace this section over here like this. So where the inductor is again a short circuit for high frequencies. Sorry, short circuit for low frequencies, open circuit for high frequencies. The capacitor is a short circuit for high frequencies, open circuit for low frequencies. As a result, only high frequencies will go through, low frequencies will not go through. So this is your high pass filter. Now in the band pass filter, things are a little different.
Regarding this filter explanation,
Yes.
actually, when you started, there was some lag. I mean, the student would have missed the initial part. So, can you repeat it?
So the initial part is nothing much. The section, the question is that what all filters can be made with L and C, right? R, L, C, what all filters are possible. And we can, so all five possible filters are possible, right? The five possible filters are low pass, high pass, band stop, and the one extra one is called all pass. Okay. Now, with one inductor, one capacitor, it's possible to build all five of these. I'm not sure about the all pass. We'll see the all pass just now. All pass, I don't think it's one inductor, one capacitor. You need two inductors and two capacitors. So anyway, so uh, the idea everywhere is that the inductor is a short circuit at low frequencies, open circuit at high frequencies. Basically, J omega L is its impedance, and the impedance of the capacitor is 1 by J omega C. So if omega is small, then the inductor is short circuit. If omega is large, inductor is open circuit. Similarly, for the capacitor, if omega is small, the capacitor is an open circuit. If omega is large, the capacitor is a short circuit. This is pretty much the idea. Right? Now, that's how you build the low pass filter. So the low pass filter at low frequencies, the inductor is short, the capacitor is open, so the circuit looks like this. Okay, but at high frequencies, the inductor is open circuit, capacitor is short circuit, so the circuit looks like this. All right. So no voltage appears across the load at high frequencies, and low frequencies pass through happily. This is the low pass filter. The high pass filter is exactly the opposite. All right. Here, at low frequencies, the capacitor is an open circuit. This is open. So the inductor is a short. So the output has nothing, right? There is no output. Whereas at high frequencies, the capacitor is a short circuit. So this is a short circuit. The inductor is an open circuit, right? So it's the previous case. And you have basically R, and the signal passes through. In the third case, now we can talk about a band pass filter. And in the band pass filter, this is going to be a special situation. We are putting both inductor and capacitor in series. Now what's going to happen? At low frequencies, the capacitor is an open circuit, so nothing will pass through. At high frequencies, the inductor is an open circuit, so nothing will pass through. But there will be some frequency in between where the combined impedance of L and C is 0. At that frequency, that resonance frequency, everything will pass through, and this is going to be a band pass filter, right? So at low frequencies, this section is an open circuit. At really high frequencies, this section is again an open circuit because of the inductor. But because of resonance, at some frequency in between, signal will pass through, and this will behave like a band pass filter. Just the same way, we can have a band stop filter. That looks like this. Okay. At low frequencies, this capacitor is an open circuit. So it's as if this branch does not exist and everything passes through. At high frequencies, the inductor is an open circuit. So it's like this inductor does not exist. Everything passes through. But there will be some frequencies in between where this will behave like a short circuit. And at that frequency, there is no voltage across the load. All right, so that's a band stop circuit, a band stop filter. Now, you can also have an alternate arrangement for this. So you don't have to put it in series, you could put it in shunt also. So keep that in mind. You can have both structures for both. So for example, I could have something like this also as band pass, and I can have something like this also for band stop. Okay, so keep that in mind. You can also have the combined of both. All right, so that's also possible. But then you would be using two inductors and two capacitors. So all of these are band pass and band stop structures. All right, and then finally, the all pass filter. I don't know if you have ever heard of the all pass filter. So this is a filter that is used only for phase correction, not for frequency, right? It passes all frequencies. So typical structure of an all pass filter is called a lattice. So this is how it's going to look. And let us not bother discussing about the all pass filter. This is completely out of topic, off topic over here. So, but this is the structure. So you can build all these filters with the help of inductors and capacitors. All pass you need two inductors and two capacitors. So this is as much as I would like to talk about filters. Now the next question is uh, I have a doubt on what process is used to find out the common mode to differential mode gain. Clearly, we are talking about a differential amplifier. And the question is, how do I find out the common mode input to differential mode output gain? And this is actually a very hard question. And that's why okay, so this is my circuit. So the common mode input, so you apply a common mode input when both V in plus and V in minus are the same. Okay, so what we are going to do over here is connect both of these to each other and apply a common voltage source as the input. All right, and now when that happens, what can we say in the small signal picture? What can we say about let's split up this current source into two current sources. Now, what can we say about the current in these two wires, in all these wires? The current in these two wires is going to be equal to 0 because you can have an axis of symmetry over here, right? You can break it up. Both sides of the circuit you are exciting equally. So the current through these branches are going to be equal to 0, which means that you are perfectly entitled to break up the circuit over here, break up the circuit over here. All right. Now, what you basically obtain is equal voltages at both the output nodes. All right. So when I apply a common mode input, if the circuit is balanced, then I will obtain equal voltages at the output. All right. I will observe a common mode at the output. Naturally, the common mode at the output is the sum of the two, is half of the sum of the two, average of the two. All right. So that is the common mode at the output, which I can now measure. So I apply common mode at the input. I obtain common mode at the output. And what is the differential output? What is the differential output? The differential output is actually 0. Right? Why is the differential output 0? Because both sides I will obtain the same voltage. Both inputs are equal. So if somebody asks you what is the differential mode output when the input is common mode, then it's actually ideally ideally speaking, the differential mode output is going to be equal to 0. But that is not what happens. All right. Why does it not happen? It doesn't happen because there are going to be mismatches between these two. And if these two are not exactly equal to each other, then these two outputs are not going to be exactly equal to each other, in which case there is going to be a slight imbalance. All right, and you will therefore observe some differential mode output. Now, what is typically done is as follows. This is not really a rigorous answer. So what you find out is the common mode at the output. This is what we can rigorously find out easily through analysis. All right. And then you say that I can quickly estimate what is going to be the differential mode output. How do I estimate? I will ask how much is the mismatch between these two. Okay. If they are 100% equal to each other, then the differential mode output is 0. But if they are not 100% equal to each other, if they are 99.9% equal to each other, right, that is 0.1% mismatch is there, then the differential mode output, the prediction is that this is going to be roughly 0.1% of the common mode at the output. If the mismatch is 5%, then the prediction is that this is going to be 5%. This factor is going to be 5%, and so on. All right. So the way you find it is you find out the common mode to common mode gain and then multiply it with the mismatch. So this is it's kind of a statistical way of finding out what is going to be the common mode input to differential mode output, this gain, that is differential mode output by common mode input gain. So this is a kind of a statistical method to find this out. uh, this is not very rigorous, so that's why I said that this is typically a hard question. Okay, now I will come to the live questions. And how have you set the question paper? Please tell us. We want to know which type of questions. I just answered this. Uh, how to proceed to become an analog engineer? All right. So I think this is a really, really hard question. I'll come to that later on. Uh, which areas we need to focus more from exam point of view? I think as I said at the beginning of this session, focus on the assignment problems. Okay. So the exam questions, I mean, we NPTEL has told us that the way to set the paper is 40 marks of recall, 60 marks of questions. So the 40 marks of recall is 20 questions, each of 2 marks. And the 60 marks of questions is 6 questions, each worth 10 marks. The 10 marks is actually 5 subparts, each of 2 marks. All right. Now, the recall questions as well as the 6 questions, the bigger questions, all of these you will find them easy if you study the worked out assignments. So, this is number one priority. All right. So, study in detail all the worked out assignments, and that will make the exam very easy for you. Uh, what changes from passive filters to active filters? All right, when do we need? All right, so what changes from passive filters to active filters? The biggest change over here is that the inductor is not a favorable component. We don't, I mean, you can make all these passive filters, right? But this inductor over here, this inductor over here, right? They don't, the inductor never makes us happy. The reason why inductors never make us happy is because it's number one, big and bulky, and number two, it's very difficult to manufacture, and number three, you don't get all the values across all frequencies. Okay, so it's a very non-ideal, very bad component, this inductor. It makes us really, really unhappy. And the only reason to go for active filters is to get rid of this inductor and replace it with something else. So there are two ways of making active filters. One is you replace the inductor altogether with a circuit that simulates an inductor. So for this you use something called a gyrator, and you make an op amp based circuit to emulate an inductor. Basically, the gyrator can convert an impedance to 1 by the impedance, right? So on one side of the gyrator, you have a capacitor, which is a favorable component, and you invert that impedance somehow with the help of a gyrator. It's an op amp based circuit, and that's how you can replace the inductor. All right, that's one way of doing it. The other way of doing it is through simulating, through emulating the signal flow graph of these circuits. So in these circuits, you can analyze the transfer function of the circuits. You can come up with the polynomial by polynomial, the transfer function, with the help of a signal flow graph. You would have learned all of this somewhere else in control theory, for example, right? So you can build the same signal flow graph with the help of op amps. So that is actually uh, uh, the better way, the better approach of designing these active filters. So these are the two ways in which active filters are made. One, replace the inductor with a gyrator based circuit which simulates the inductor, and the other is you emulate the signal flow graph of the circuit using an op amp based circuit, op amp and RC. So that's why you want to go to active circuits and not have passive RLC filters. Uh, is there any negative marking? No, there is no negative marking. Exam is MCQ type. It is not short answer type. All the questions are MCQ type. Uh, then I have another question by Anant Arya saying that when do we need a freewheeling diode across an inductor? So this freewheeling diode business. All right. So an inductor, the property of the inductor is that it likes to keep the current through it a constant. So if you are having an inductor which is carrying a current, right? Let's say I have an inductor which is carrying a current. And suppose I have a switch along with it. And I suddenly jerk the switch open, throw the switch open. Then what is going to happen to this current? Right? Suppose this inductor was carrying some heavy current. Let's say the application is probably a DC to DC converter, or the application is an inverter, right? Power electronics kind of application, right? This is where these things normally happen, right? You have an inductor carrying current and you have a switch in series with the inductor, and suddenly you throw the switch of the switch open. Where is this current going to go? Now, if you don't give a path for this current to go, then what is going to happen? You will have a huge spike of voltage over here because of L di by dt. Right? Di by dt is now going to be negative. All right. From huge current, you are suddenly going to zero current. So you will get a minus potential drop across the inductor, which means that the switch end of the inductor is going to get a huge potential spike. Now, this potential spike can be big enough that it will ionize the space in between this switch and the gap of the switch. So typically the switch will have a gap. When you throw it open, there will be some air, right? You have broken the switch open, so there is an air gap. So what's going to happen is when this potential suddenly builds up, right, you get this huge spike of potential. The gap of air is going to ionize, all right, with this huge buildup of potential. Once it ionizes, it is going to break down, and then if it breaks down, basically there will be a spark across this switch and current will flow. So this is what typically happens. All right. And why is this bad? This is bad because the after a few throws of the switch is going to degrade. The switch is going to become black and it is going to burn out. Right. So you don't want this to happen. The life of the switch is precious. Okay, so this is when you throw in something called a freewheeling diode, which is basically a diode in feedback, right? And this diode is normally not doing anything, it's reverse biased. When this side is plus, this side is minus, this diode is reverse biased, it's not doing anything. But when you throw open this switch, this diode, for example, if this voltage builds up, then this diode is going to start conducting and take away the current before the air gap across the switch ionizes. So this is the purpose. This is where you you use a freewheeling diode. This is the reason. This is the responsibility of the freewheeling diode. Its job is to carry this current through. Okay. Uh, what other questions do I have? Indu Kumari is asking me, uh, please explain curve centering in band gap reference. I think that's kind of outside the scope of this course. The band gap reference is not really part of this course, but nevertheless, let me try to explain. So, no, the question is different. The question is, please explain curve fitting in band gap reference. Okay, so uh, I don't want to get into too many of the details of the band gap reference, but the idea in the band gap reference is as follows. You have you will typically have two different circuits or two different paths in one circuit. One path is going to produce a voltage which goes up with temperature. Another path will produce a voltage which goes down with temperature. And then what you have to do is you have to adjust these slopes such that they are negative of each other. Add them after you have adjusted these slopes such that they are negative of each other. When you add them, what will you get? You will get something that is a constant at the point that you made this adjustment. So if you made this adjustment at this point, then at this point there will be some curvature. So this is what you do in the band gap reference. Okay. Now you have to choose this point judiciously. Number one, choose this point at the center of your total temperature range. So that is called centering. So if your temperature range is from to 80 degrees, then this point should be at 40 degrees. Whereas if your temperature range is from minus 40 degrees to 120 degrees, right, then this point should be at again at 40 degrees. If your range is from 0 degrees to 120 degrees, this point should be at 60 degrees, and so on, right? It's at the middle of your temperature range. So that is your centering part of the story. And then your curve fitting, the fitting part of the story is basically you have to adjust the slope of the one that is rising with temperature to the one that is going down with temperature at that point. All right, so this is pretty much the story over here. How we do it and so on is typically with the help of a few extra components, resistors, and so on. A little bit about the frequency response of a basic power amplifier and transit frequency, FT. Okay, so FT is something uh, I don't know if you have come across something like this, but the definition of FT is something very special, right? This circuit is going to look crazy, right? I'm applying a current source at the gate of the MOSFET. Uh, so it's really going to look uh, uh, totally crazy. But the thing is that this current source is a small signal current source. It's not a large signal. It's not DC. So that's what you have to keep in mind. Now, so FT is defined as the frequency at which the current gain is equal to 1. All right, so this is the experiment that you have to do. right? This could be a MOSFET, it could be anything else, it could be an amplifier, it could be anything else, any other component, it could be a BJT. It doesn't matter what is inside this, right? It's a box, two port network. So the frequency at which I out by I in becomes equal to 1. Presumably this two port network is an amplifier. Okay, presumably it's an amplifier. If it's not an amplifier, then FT is out of the question. Okay, only if we are talking only if this two port network is an amplifier. So the frequency at which this is called the current gain drops to 1, that is the frequency which is defined as FT. So this is the definition. The frequency at which I out by I in magnitude is equal to 1. Now why is this important? It's important because beyond this frequency, you will not be able to get a power gain from this circuit, right? It might be worth your while to directly connect the load to the input source, then have this two port network in between, right? I mean, why do you put the two port network? Because you are looking at a power gain. Any amplifier is actually a power amplifier. You're actually amplifying power, whether it is a common source amplifier or a common gate amplifier or a common drain amplifier. You're actually amplifying power. All right, it doesn't matter how you look at it, eventually you're just amplifying power. Now what does power amplification mean? Power amplification means you're taking in extra power from the supply and delivering it to the load. All right. Now, this circuit will be able to do that only till the frequency FT, only below the frequency FT. Above the frequency FT, it's better for you to directly connect the load voltage to I in, to your input source. All right. So eventually what is going to happen is you won't have I in, you will have a voltage source with a source resistance. This is the use case, voltage source with a source resistance, right? And over here it's not going to be a short circuit. Over here there is going to be RL. Now in a general, if you want, if you don't have this two port network, then your output voltage will be RL divided by RS plus RL, if you don't have this two port network. And from that you can figure out what is the power delivered to the load. Beyond the frequency FT, where the at FT the current gain becomes equal to 1, beyond that frequency you will not get any power gain at all. All right, so that's pretty much the story with FT. For the MOSFET, we have studied only MOSFETs. If you think of just one MOSFET as a power amplifying device, then FT works out to GM over CGS. All right, you do this experiment with a MOSFET, you do the small signal analysis. I think it was there in one of the uh, assignment questions also. You do this small signal analysis, you will find that FT is nothing but GM by CGS, omega t, not FT. So you have to convert this with the factor 2 pi. Okay. What is power supply rejection ratio in an op amp? Power supply rejection ratio in anything is basically, the concept is like this. Uh, what is the signal coming from the input? That is the desired signal. Okay, you want it. So if the output contains signal coming from the input, then that is good. If the output contains signal that is coming from elsewhere, for example from the power supply, then that is just bad. All right. So power supply rejection ratio is defined as the gain that you see from the input. So I have, think of your circuit as a 3-port network. So far we have been talking 2-port, right? At port 1, I have the input. At port 2, I might have some noise coming in from power supply. Maybe some ripple or some noise, all right? And I have the output. So I have a gain from the input to the output, right? Let's call it, this is the desired one. Let's call it a desired, AD. All right. And I have some gain from the power supply to the output. Some voltage gain is there from the power supply to the output. So let us call this a not desired or a noise. All right. Suppose I have applied 1 millivolt at the input and 1 millivolt at the power supply. Then the output will contain 1 millivolt times AD plus the noise times AN. Okay. The question is, what kind of input will overcome the noise? What should be the input, so that what is the relationship, or rather what is the minimum input at which I will be able to overshadow the noise? Okay, that is the metric. All right. If you think of signal to noise ratio, for example, right, what is the minimum signal at which you will overcome the noise? Okay. So in a similar way, in a similar fashion, what is the minimum input at which at the output I will have more signal than the input? Sorry, more signal than noise. That is the question, right? So what I look at is the factor AD by AN. And this is defined as power supply rejection ratio. This is the definition of power supply rejection ratio in any circuit, op amp, not op amp, anything. All right. So it is how much is AD more than AN. If I have two equal signals over here, then at the output I will have AD times 1 millivolt and I will have AN times 1 millivolt of noise. What will be my signal to noise ratio then? In other words, if my power supply noise is 1 millivolt, what can my input be? How low can my input be? My input can be AD by AN lower than 1 millivolt. I will still be able to compete with the noise. Okay, so that is the definition of PSRR. So PSRR for any circuit is basically this voltage gain from input to the output divided by voltage gain from power supply to the output, small signal. The source of this noise can be many different things. It can be ripple, right? Maybe the power supply is being generated by a DC to DC converter. That will have some ripple. Maybe it is coming from a rectifier. That will have some ripple, right? Maybe it is coming from a battery, but you're also driving digital circuits with this, and they are drawing power periodically, right, with the clock, and that is causing a drop in the power supply periodically. So that is causing digital noise to get injected into the power supply. So there are many sources of this noise. Maybe this noise is coming from interference, right? There is maybe some a cell phone tower close by that is broadcasting something, and that is creating, injecting noise into your power supply. So there are many sources of noise, right? You want to see You're basically PSRR is a metric of how much does your circuit reject noise that comes in from the power supply. Okay, you're not supposed to amplify noise coming in from the power supply. You're supposed to amplify only the input. Fine. Okay. uh, um, Need of the current source at source terminal in diff amp circuit. What is the need of the current source at the source terminal of the diff amp circuit? Over here, why should I put a current source over here? And the reason why you put it over here is as follows. You put it over there because you want differential gain but no common mode gain. Okay, again, similar to the story with the power supply rejection, you want to reject the common mode also. So if this circuit is balanced, if this circuit is balanced, okay, then what happens? In differential mode, these voltages are ground at differential mode. But in the common mode, you basically split it up into two current sources. Let's say it's not a current source. Let's say there is something over here. But you split it up into two of those halves. And you disconnect. Right? And that's your common mode circuit. So in the differential mode circuit, this is what you have, which is basically a simple common source amplifier. In the common mode circuit, this is what you have. And something is there over there, maybe not a current source, right? Something. I want to find out what is that something. Now, if you want no gain in the common mode, you want no gain in the common mode, then what should this be? This should be a very, very, very large resistor, right? That's the only way that you will get no gain in the common mode, because then effectively, the source has been disconnected. It's no longer a common source amplifier. All right. So that is why we place a current source over there. Now you would say that why place a current source? Place a very, very, very large resistor, right? Unfortunately, it's not going to work, because if you put a very, very large resistor over there, okay, very good, but you won't have any swing, right? Remember your swing limits. Your swing over here is going to be severely limited because you need to have a certain current over here. But if you have a very large resistor, then this voltage is already becomes very large. All right, so you really can't have a very large resistor. You would like to have a current source. However, the general principle applies. If you can find a way to use a resistor over there, please go ahead. Don't use a current source. All right, current source is the most convenient. In RF circuits, for example, at very, very high frequencies, the most convenient is not a current source. In those cases, we actually place an inductor. Right? Remember, the inductor has the property that at DC, the voltage across the inductor is zero. It's a short circuit at DC. But at high frequencies, it's like an open circuit. So we use that property of the inductor and place an inductor over there instead of a current source, because the current source doesn't work at at high frequencies. RF frequencies, right? So you can't really operate the current source at those frequencies. So therefore, we sometimes use an inductor over there. So feel free to do that. The inductor, of course, is big and bulky, and we need to have ways to manage the show. But it turns out that at RF frequencies, the inductor becomes small. As frequency becomes higher and higher, the size of the inductor also becomes smaller and smaller. So it's possible. All right. So does that? I hope that answers your question. Um can you please no describe the utility of compensation in op amps? All right. So I don't know where you are, but where I am in Delhi, and in Delhi it is now almost winter, and in winter we like to have a bath with hot water. Okay, so how do you have a bath with hot water? So you go to the bathroom and you have two taps. One is the hot tap, one is the cold tap. Right, and now of course you can have a bucket and fill up enough hot water in it. You can fill up enough cold water in it and adjust the temperature that so that it's just right, and then you can have your bath. That's one way of doing it, right? But that's not the luxurious way of doing it. The way I like to do it is to have a shower. Okay, in summer I have a shower, so in winter also I would like to have a shower. All right, so the shower is on top. Now the pipe, so this is overhead. The shower is overhead, far up on the near the ceiling of the bathroom, right? So there is a long pipe from here to the outlet of the shower. There's a long pipe from here to the output of the shower. Okay. So what happens? I first switch on the hot water shower. All right, I turn this on. Initially, there is a lot of water inside this pipe, and all of this is cold water. Okay, so initially cold water starts coming out. Now when all the water in the pipe is exhausted, then the water from the geyser starts coming out. All right, till then I'm still getting cold water even though I've turned on only the hot water shower, right? So after all this water is exhausted, then I find that the water, so first the water was all cold, then when it's all over, then the hot water starts coming out, but now it's piping hot. All right, because it's coming from the geyser and there's no cold water mixed. So now I turn the cold shower on. All right, what happens now? Now suddenly there is cold water coming in from here, right? And I find that the now the water temperature mixes drops drastically. Okay, so I have probably switched on because I felt too hot. I must have turned on the cold water too much. Okay, so what happens is now suddenly I get only cold water because there is a huge rush of cold water. So then what do? I'm going to decrease the cold water. Again, it becomes very hot after some time. Why is it happening after some time? Because this pipe is very long. All right, so whatever action I take now, the result comes after I exhaust the water in the pipe, after a lot of time, after a huge lag. Okay, so I again turn the cold shower down. Again, the water becomes very hot. So then what do? I turn the cold shower up again, then it becomes very cold, right? Desperate, what do? I again turn it, I switch off the cold shower. Now it becomes very hot. Desperate, what do? I switch off the hot water. I switch on the cold water, right? So all I'm doing while trying to have my luxurious shower is I'm just adjusting the knobs, trying to figure out which is the right temperature. And trust me, it just doesn't work. Okay, you will not be able to get the temperature right. And why? Because the time that you take the action and the time that the result comes out, there is a huge delay in between. Now, this is exactly the same story that happens in our amplifier. All right. So, an amplifier. So, you've got this amplifier, and the problem is the delay in the amplifier. Whatever input comes, if the output happens exactly at the same time, no problem, right? You don't need any compensation or anything like that. All is easy, right? It will work just fine. The problem is that there is a long delay between the input and the output. Sorry, my arrow should be one way. All right. Now, this amplifier, if I use it just by itself, then again, no problem. But I'm never going to use just by itself. I will have a feedback, right? Like I have in the shower, I have a feedback through my body, right? I am feeling the temperature and trying to adjust the knobs. So the problem comes only when you have this feedback, right? Not when you have it open loop, right? So for example, if I if I put an inanimate object inside the shower, it's fine, right? There is no problem. You hold it under the tap, it's done. Only when there is feedback, when I am feeling the temperature and trying to adjust for the right temperature, that is when the problem is. All right, and the problem arises because of delay. So what do I have to do? How do I fix it? I have to somehow get rid of this delay. If I can get rid of the delay, then I can take a quick corrective step. If I can take a quick corrective step, then this will correct immediately and no problem. But if there is a delay, then my correction comes after some time. And then what are you going to do? You are going to do an overcorrection, right? And then again, it's going to go back, right? So you are going to oscillate back and forth, back and forth, back and forth. Okay. So this is basically the idea of compensation. In compensation, what are you trying to do? You're trying to fix this delay, right? So what do I have in my amplifier? I might be having two stages. All right. Now these stages, the problem is that they all have, I mean, if the circuit is has no capacitance in it, then no problem. Then there is no delay. But the circuit has capacitance, right? Capacitance means there is some RC time constant, and that means that there is delay. So there is some delay in the first stage, there is some more delay in the second stage. And now the only way to correct it is to fix the delay. How do you fix the delay? You can short circuit one of the two stages. Right? Remember, the capacitor is like a short circuit at high frequencies. Right? So this capacitor, this compensation capacitor, will behave like a short circuit, and it will kill the delay in the circuit by shorting these 2 points. Right? If you short these 2 points, then one stage is gone. Right? One stage of the amplifier is gone, and therefore you have reduced the net delay. So this is pretty much the idea behind compensation. This is why the capacitor is put there in the first place. Okay, so that's basically the answer to your question. And what else do I have? Um, how small should be the small signal for applying a small signal model? Yeah, there is no how small. If it's not small enough, then make it smaller. That's the answer to your question, right? In if you want to talk mathematically, then your answer is that it should be infinitesimally small. However, infinitesimally small is not going to do anything for you, right? So you want to have some amplitude at the input, but if you're not happy, if you think that that amplitude is large, then make your amplitude smaller. Now then you're going to ask, why will I not be happy? Okay, so that is going to be your question. Why should I ever not be happy? So therefore, can I apply a large signal? The reason for not being happy is distortion. So what happens is your output is going to start clipping because of the swing limits. Okay, so if your output is going to clip because of the swing limits, then you are applying a signal that is too large. So make it smaller. All right. So I hope that answers your question. Mathematically speaking, the answer to your question is infinitesimally small. But practically speaking, you can go as small as, I mean, you can basically make sure that the swing limits are okay, and then you can deal with it. All right. So there are a few more questions that I don't want to answer. It's beyond the scope of this course. What is EMC, electromagnetic compliance? And can it be achieved with the help of filter? The answer is yes. You can achieve electromagnetic compliance with the help of filters. Um, I mean, there are a lot of sources of noise, right? Um, then there is a question on full bridge, dual channel H bridge, and a simple H bridge. And frankly speaking, I don't know what this question means. I cannot answer your question. Uh, there is one more question. Will our exams be conducted offline? When would we be updated with our centers? And I don't know the answer to your question. You have to contact NPTEL for this. Uh, then I have a few more questions. Uh, One is, how do we proceed to become an analog engineer? Another is, what are the best opportunities for an electrical engineer after clearing GATE? And another is, how to proceed to become an electronics engineer. Currently, I am in third year of BTech. All right. And there is one more question. So, uh, there is one. No, this is all. This is all. Okay. So these questions are basically for your career, right? So in terms of your career, I would like to spend 2 minutes at least over here. Uh, it's like this. Analog circuits happens to be one area of electrical engineering where you need to understand all of electrical engineering, right? Only when you understand everything, starting from device physics, power electronics, electromagnetics, uh, power systems, control theory, signal processing, computer science. When you understand all these, then only you can become a complete analog circuit designer. Okay, so we are at the top. If you think of electrical engineering as a pyramid, we are at the apex. Okay, so the analog circuits designer is at the top of this pyramid. We are at the apex. All right. It also turns out that the analog circuits designer is, uh, one of the most important people in the chain towards any product. So let's say you have a cell phone, right? Without the analog circuits engineer, you can't make the cell phone, right? Who is going to make all of your circuits? So all the circuits eventually have to come through the analog circuit designer, even the digital circuits. All right. If you are trying to design a computer, yes, microprocessor, yes, several digital circuit designers can do the stuff, the basic stuff. But at the end, the analog circuit designer is absolutely required. Okay. There is more analog to digital than there is digital to digital. Okay. Even in digital design, there is more analog than actual digital circuits. If you are thinking of communication, just talked about a cell phone, uh, and of course, any kind of system design, analog circuit designers are really really important. Now, what I am trying to do over here, I'm not really trying to answer your questions. Right, your questions are some other questions. My answer is something else completely. My answer is that, don't take this as an answer, right? My point of view is that be an analog circuit designer. This should be your objective, right? Because if your objective is up there to reach the top of the pyramid, then you have understood all these other stuff, all everything. You're on top of everything, right? Uh, it's also something like this. Analog circuit designers typically have the highest salary, right? Analog circuit designers are typically the most desired, the most coveted in the industry, right? They're also the rarest species. So it's hard to be an analog circuit designer, but then that should be your objective, because once you reach there, you are on top of entire, electrical engineering, computer science. You are on top of everything. Okay, so that's how I would really like to answer your questions. But how do you proceed to become an analog engineer? I don't know. Right, there are all these issues over here, like luck, like what are your career opportunities that come by, right? Which companies do you interview for, right? Who actually recruits you? And not just that, who is your boss in the company, right? So there are a lot of factors that play. How do you end up growing in your career is not really all the time. uh, I mean, you can't follow a certain set down career path. There are all these other things that come by, right? For example, if you, let's say you join a company named Analog Devices, which presumably makes analog circuits, right? Because its name is Analog Devices. They make digital circuits also, just by the way. Now, if you join the digital circuits group in analog devices, then you don't end up being an analog engineer. But if you join the analog group, and let's say, so you have now a chance. Now, this boss of yours, he says, all right, design this DC to DC converter. So you design one DC DC converter. Then he says, all right, design one more DC DC converter. So day after day after day, if he makes you design DC to DC converters only, then that's not learning analog circuits, right? So you have to make sure somehow, how I don't know, but you have to make sure that you have to broaden your base. You have to, design DC DC, tomorrow design op amps, day after tomorrow design band gap, day after that design. No, you have to get into all these different things, right? And that can happen only when the stars come together, when everything is aligned nicely. You basically get into this analog profile. Number one, you have a good boss who gives you all these opportunities. When all these things line up, then you end up becoming a real analog circuits designer. Okay, so there is a lot of luck, there is a lot of alignment of stars that can happen. uh, all these together, it all has to happen, then you become an analog engineer, that if you want to proceed with the career path, right? But the biggest thing that you need is the desire. You have to want to become an analog circuits designer, right? If you want, then I am sure these stars will line up eventually. Okay, so the biggest question is, do you want? If you want, then it's possible. They will line up. So I hope I have answered all your questions. Uh, yeah, so we have overshot in time, uh, and I think we can close now. Are there any other questions, Shweta, Raghav?
Sir, yeah, there is one more question. I just wow.
There is a one question. Can we interchange PMOS and NMOS in CMOS inverter?
No, we can't interchange PMOS and NMOS in CMOS inverter. Uh, it looks like you can, but you actually cannot. It is not going to work, right? The PMOS always pulls up, the NMOS always pulls down. Something that pulls you down has to be below you, something that pulls you up has to be above you, right? The PMOS and the NMOS cannot be interchanged. Yeah, that's all.
Yes, sir. We can close now.
Okay, thank you everyone. Thank you for registering for this course. Thank you for suffering through this course, and hopefully you will all do well in the exam. And uh, even more importantly, hopefully I have given you a seed and in your head to drive you towards sockets. I have hopefully given you some little bit of desire to become an analog circuit designer. Okay. Thank you, everyone. Thank you.
Thank you, sir.